Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Before we start, I would like to introduce myself. My name is Beta Cahaya from Chemical Engineering Department ITS. I would like to present my research about solar-driven water purification for sustainable clean water supply. This presentation consists of four sections. First, introduction, second, method, third, results, and fourth, conclusion. First, introduction. Is a maritime and tropical country, and also with clean water problem. As for the largest population, clean water demand is unequal with its supply. Back again, as a tropical country, it is easy to find coconut tree. Coconut coir are known contain diverse compound, and top compound is cellulose. It is about 23 and 40%. But the utilize of coconut coir are just stock for plant growing media or host appliances. While cellulose has so many properties: biodegradability, high porosity, high surface area, and also low density. Fausia 2090 utilized cellulose from coconut coir as cellulose aerogel as oil absorbent. That's why we decide to applicate the cellulose aerogel from coconut coir as bilayer solar steam generation system. Is inspired from two different research. First one is Fausia 2090, synthesis of cellulose aerogel from coconut coir with its ability to absorb oil. The second one is Gazami et al. 2040, the idea of creating bilayer SSG system which composed of porous layer and fototermal material. Materials and method. Material we use are coir fiber collected from coconut mills in Tulungagung. Second, sodium hydroxide and ammonium hydroxide purchased from Merck's. Ethanol purchased from PT Indo Aji Datama. Urea purchased from PT Petrokimia Gresik. Black ink purchased from Epson. Pulp, the lignified pulp then mixed with ammonia and urea. It is cross-linker, then sonicate for 30 minutes, then dilute at -5 °C for 24 hours. Coagulate using 96% ethanol for 24 hours. Solvent exchange using demineralized water, freeze dry at 20 Pascal for 7.8 degrees Celsius. Freeze-dried cellulose aerogel, then coated using black ink to become the layered SSG system. Gel characterize its crystallinity using X-ray diffraction. Aerogel ability to transfer water test by William test standard number 2.6. Thermal conductivity measured using ASTM D5470. Evaporation test using solar simulation for 3 hours. Last measures its density and porosity. Water evaporation experiment were carried out using solar simulators and a lamp 300 watt at room temperature. The prepared SSG system consists of cellulose aerogel and ink was put on the surface of salt water in 50 milliliter beker glass. The salt water contained of 3.5% sodium chloride. The beker glass was placed on the top loading balance to measure the weight change of water evaporation. Third result. The appearance of cellulose aerogel was shown in this picture. Cellulose aerogel is lightweight and also porous. After that, cellulose aerogel coated using black ink as a photothermal material. Action pattern of pulp has two characteristic peaks at two key of 16.121 degree and 22.23 degree that match the standard of cellulose type 1. Different diffraction pattern was obtained for cellulose aerogel, in which the peak appeared previously in the diffraction pattern of the pulp disappeared. The peaks were replaced by three characteristic peaks at 11.592 degree, 16.021 degree, and 22.170 degree, which match the standard pattern of cellulose type 3. The maximum porosity was obtained at ammonia volume of 8 milliliter with a porosity approximately 98.7%. As expected, the porosity influenced the property of cellulose aerogel. Water pumping capacity and thermal conductivity. The water pumping capacity increased from approximately 0.6 centimeter per minute at porosity of 96.7% to 0.63 centimeter per minute at porosity of 98.7%. Meanwhile, the thermal conductivity increased from 0.143 watt per meter Kelvin at porosity of 97.6% to 0.4 at a porosity of 98.7%. The value of thermal conductivity for all cellulose aerogel have a different porosity in still in the typical range of good insulating material. We also did evaporation tests with the aerogel material to compare cellulose aerogel ability as SSG system. The evaporation rate of water under one sun illumination with the presence of incoated cellulose aerogel was about 0.47 liter per square meter hour. It is increased significantly when the self-floating incoated cellulose aerogel was placed on the water surface and reached the highest evaporation rate of 1.062 liter per square meter hour. It is clear that the porosity has a great effect on the evaporation rate. This may be related to the capability of aerogel to capillary pump the water from the reservoir below the aerogel. As discussed before, the pumping capacity increased with an increase in porosity, and the highest pumping capacity obtained at porosity of 98.7%. In addition, it may be also related with the thermal conductivity of the aerogel, which serve as thermal insulator to avoid the heat loss. To check its ability, we also did an experiment of water evaporation test under real sun from 7 a.m. until 3 p.m. It is clear the cellulose aerogel could evaporate the water in the beaker. The condensed vapor was taken to acrylic housing, then trapped to the bottom of the acrylic housing. Last pic showed the water level decrease after the test, which showed by the red line. Fourth, conclusion. Conclusion. First, the cellulose aerogel derived from coir fiber can serve well for two main functions. First, water transport and thermal insulator. Second, it is characterized by the low density, low thermal conductivity, and high porosity. Hence, the cellulose aerogel can have the ability to float on the surface of the water, where it can still transport water from the reservoir to the surface of the photothermal material. As the porosity of aerogel cellulose increases, the rate of water rise also increases. The faster the water is evaporated, and the higher temperature rise in the surface layer. Acknowledgement. This work has been partially funded by Kurita Water and Environment Foundation, Japan through Overseas Research Grant Program. Thank you.